Okay, now this next section talks about pre-images. Now what in the world is a pre-image? Well, to introduce this, let me go back to the cartoons section. So hang on a moment. All right, if you remember this picture back in the, as I said, back in the cartoon section, here you have the domain, here you have the codomain, and you have this diagram showing that elements of the domain map to the codomain. Now notice that these two vectors map to the same vector here. So here we have a set. We have a set of vectors in U that maps to a single vector in V. So this set is called a preimage. And it's a set. It's not necessarily a single vector. In this case, the preimage is a single vector, but in general, it's going to be a set. Right? So in this section, we'll talk about properties of preimages. So that's the intro. Here's the formal definition. Suppose I have a linear transformation from U to V for each individual vector V in the codomain. Define the preimage of V to be the subset of U given by the set of vectors U in the domain U that map to the vector V. All right, so in other words, T inverse of V is the set of all those vectors in U that get sent to the vector V. Now, notice that T inverse of V can be empty. If you go back to our cartoon picture, here, the preimage of T is empty. So this has empty preimage. So that's quite possible. But that's no problem because empty set is set in its own right. Okay. All right, so let's look at some examples. Consider the linear transformation from, we're getting fancier here, so we're taking linear transformation from a set of three-dimensional vectors to the 2x2 matrices. Defined in this way, okay, you can see from here that T is defined on a set of basis vectors. If I put 1, 0, 0 here, I'd get one matrix. If I put 0, 1, 0, I'd get another matrix. 0, 0, 1, I'd get another matrix. It turns out that if I choose this matrix here, you can verify that, well, actually, we're not going to verify it. We're going to find the preimage systematically. So we're going to find out all the vectors U1, U2, U3 that give us this matrix here. So the condition is that U1 minus U2 should be equal to 2. 2U1 plus 2U2 plus U3 should be equal to 1. 3U1 plus U2 plus U3 should be equal to 3. Minus 2U1 minus 6U2 minus 2U3 is equal to 2. For us, that's a piece of cake. We have 4 linear equations. And we want to find the most general solution. So we set up our augmented matrix and we solve it. We find out that it has rank 2. We can use this to find the most general case. Now we have 2 non-pivot variables. We can see that the solution set is going to be two-dimensional. Two-dimensional set. Okay. We can characterize this set using the two free variables, and it turns out that this result, actually I need to catch myself, this is not a free variable, this is the constant vector here, so we have one free variable. One free variable. Okay. Hope you caught that. But we have a single free variable here. We can express the solution set as a one-dimensional, as a constant vector plus the span of a one-dimensional vector. Okay, so that shows us that we have basically a, well, this preimage is not a vector space because it's not a span, it's a constant vector plus a span. So in some ways it's kind of a displaced vector space. Okay. All right, so here's one example. Let's look at a different one. Let's look at a different one and compute the preimage for this one. So similarly set up the set of equations. You do exactly the same thing. Now when you do the row reduction, it turns out that there's no solution. So here we do have a case where the preimage is the empty set. Okay, so we have examples of what I did mention would be possible, that you can have a case where the preimage is an empty set. Okay, so let's go on to this new section, new linear transformations from old. So turns out we can create more linear transformations from the linear transformations that we have. So we've created a monster. We can combine linear transformations to form new linear transformations. For instance, if I have two linear transformations between the same two vector spaces, I can define the sum of these two linear transformations. Now you can see that we've already identified matrices with linear transformations. So really what we're talking about is matrices. You can take the sum of two matrices to get another matrix. Same thing that you can do with matrices, you can do with linear transformations. You're going to see also that you can take arbitrary linear combination of matrices, means you can take an arbitrary linear combination of linear transformations and still get a linear transformation. So that's what this section is all about, showing that if you take the sum of two linear transformations, it's a linear transformation. You can go ahead and check the linear properties for the sum of those linear transformations. Of course, the next one is going to be the scalar multiple of a linear transformation is a linear transformation. Okay. You can work through those examples, and there's a similar proof for this one. Show the scalar multiple of a linear transformation does have linear transformation properties. And here's an example of that one. All right, now we've been talking about linear combinations of linear transformations, and we know that linear transformations are like matrices, and we know that matrices themselves form a vector space. Okay, matrices themselves form a vector space. So that suggests that linear transformations form a vector space, and in fact that's true. Now we've shown already closed under scalar multiplication, closed under addition. We can go through and show all the properties of vector space hold for the set of linear transformations. And really this is the very same proof that we showed that matrices form a vector space. So we can talk about the vector space of linear transformations. So that's really quite interesting that linear transformations started out as functions between vector spaces, and now we're showing that linear transformations are a vector space themselves. Now, since we can have linear, so we can go one further. We started out with linear transformations are functions. Now we show that linear transformations form a vector space. So we can talk about functions between linear transformations, because linear transformations themselves are vector spaces. A way to define functions between linear transformations is, one way is to take the composition of linear transformations. For instance, if I have a linear transformation T and another linear transformation S, I can transform the linear transformation T into another linear transformation by taking S composed T. Now it's also going to be a linear transformation. And you can go through and show the properties that if you compose linear transformations, you still get a linear transformation. So composition of linear transformation is like matrix multiplication. We know that the product of two matrices is a matrix, and that's analogous to this result that the composition of two linear transformations is a linear transformation. Go through and check the same old results. Do some examples where you show that the composition, again, the composition really is just matrix multiplication. I sort of spilled the beans here. I guess he wants to show that later, but it is true that the composition of two linear transformations corresponds to the multiplication of the two matrices that define those linear transformations. And we'll be talking about that more